If you recall, yesterday we had very quickly, of course, we had gone with these slides and we had defined the H and the alpha, okay, that you recall, but this was onto the horizon. Okay. Then we also went on to define on the standard coordinate system, okay, that was on the equatorial coordinates, where you see your equatorial plane to be the plane of the reference. Okay. So we define here, if you recall, again declination that we put as delta and our angle as tau. Okay. Keep these things in mind, but we will not talk about these things anymore, but we will talk something else, but we will use this information with little knowledge that we have got about astronomy. Okay. Now, just remember that what we are trying to do is to estimate R, okay, and the R in the table, because that R will tell me if my insolation is strong, moderate or light. Okay. So, with this background we will try to estimate the R. Okay. And if I ask you what are those parameters, factors on which R could depend, okay, so you will answer me what time of the day we are talking about, right? So that's the first thing. Okay. You will also tell me where are we? Are we sitting in London, or we are sitting in Kanpur or Banaras? Okay. That is so. And then you will ask, okay, what is the longitude of the place, the latitude of the place, the time of the day you are talking about, and in addition to time of the day, you also will say what is the date, what is the day, is it the January 1st, okay, or it's a December 31st or June 25, because solar radiation, just as hunch, you will say that will depend on these things. Okay. Where you are, that is longitude, latitude, time of the day you are interested in, okay, and day of the year. Okay. So with that background in mind, we will try to do something so that we can calculate the R. Okay. And the first thing for that we need to define is, so the time, you say, well, I want to find out what is the stability or what is the incoming solar radiation at some particular time. Okay. You suppose you said, let us say 11 o'clock in the morning, okay, but you say 11 o'clock, is this 11 o'clock in real sense, is it really 11 o'clock? This 11 o'clock is really with reference to some standard meridian, okay, that is our reference point. Okay. When I am saying 11 o'clock, it is really 11 o'clock at the reference meridian, right. So suppose what is the reference meridian in India for the time to measure the time? That is in, I haven't written there, that is, I will tell you exactly, 82 and I will tell you exactly, just because these numbers you do not have to remember them. Okay, here you go. 82 degrees 30 minutes, okay, 82 degrees 30 minutes east, okay, that is the reference meridian I have, and internationally the time is measured through Greenwich Mean Time. Okay. For example, friends from France, their reference meridian will be the reference meridian passing through the Greenwich. Okay. But this is the reference meridian when sun is right on top at this place, all over the India this is 12 o'clock. Okay. But in actual sense, okay, is it really 12 for us? No, because if it is a 12 o'clock, let us say at Allahabad, in terms of the radiation which I am getting, it might be what? Less or more? Less. It may be something like 11:30 for me, whereas at Allahabad it is already 12 o'clock. Okay. So when we are doing the actual calculation, so we have to take the actual time. We can't take the standard time. Do you agree with me? Okay. If that is a point, and this is at Allahabad. So the time when you want to find out the stability or incoming solar radiation, you have to modify your time. Okay, and that modification is what you see is a change in the time. You see here, this is the local meridian and this is the standard meridian, okay, divided by 15, okay, and that this is the time you will get in terms of in hours. Okay, so we have to, first thing we have to immediately correct, is it our time? Okay, is that part clear? Okay, if that is clear, now I'll ask you another thing. $12 on, let's say, June 30, okay, and 12 o'clock, let's say, on December 25th, okay, even after correction, in terms of the solar radiation, are they same? No, they are not the same. Then it means it also depends on the position of sun, okay, right. So somehow we have to change the time, okay, based on the position of sun. Okay, I'm just developing the argument so that it's easy to understand. Okay, so what we do normally, we take average position of the sun and time is defined. Okay, but in real sense, the actual time will depend on sun's position, right? Okay. Sun's position will depend on what? The day of the year I am talking about. Okay, because sun's position will be variable depending on the day of the year. 1st January, 30th January, they all will change. But actually, when the time what we see in our watch or something, that is all mean, depending on the mean solar position. Okay, but we are trying to do a more accurate job, so we have to have something what we call as the equation of time. Okay, so what I'll show now, the next one is the equation of time. Okay, and that shows equation of time. It really shows that the difference between the mean solar time versus apparent solar time, and what we need is apparent solar time, the time which is existing right now because of the day which I am referring to. Okay, so the other correction which I must do in my thing is based on the equation of time, and that is what you see here, equation of time, EQT, and I'll pass on this all the information to you, don't worry about that. Okay, and we will also explain you what these are. Okay, so equation of time, you see the two corrections that I must do in my time. Okay, so here what you see here, the larger n, okay, is number of days in the year. It could be 365 or 366, okay, depending on which year you are talking about. And the small n, as you see here, is, that's what we call as Julian day. Okay, it means it is a day starting from January 1st as 1st and let's say February 1st as 32. Okay, so that is by Julian day, counting from day 1 as January 1 and going up to 365 days. Okay, it's not difficult to derive this equation, but we'll somehow not do that one. So, but you can find out the equation of time. And what is this really? This is the difference, okay, because of the position of the sun, okay, because from difference of the mean position to the apparent position. So, this correction also, when you want to find out the actual time of the day, we should correct based on the EQ2. So, all variables you understand here, n and small n, that is all I need to know. Okay, okay, good. Okay, now I can say what is my apparent time, or time which is more useful, more meaningful for me to find this solar radiation. Okay, agreed? Okay. So what you see here is the apparent time. So this is the time, whatever time you are referring to, okay, suppose 11 o'clock, but this 11 o'clock is based on the standard time. This must be corrected based on to your local meridian, right, okay, and this should also be corrected based on to the Julian day, because solar radiation will depend on the sun's position, okay. So that is how you find this is your really your apparent time, or if I can say it's your real time, okay. But of course we have, for the convenience, we have the standard time or reference time, but we are trying to estimate something else for which I need apparent time. So this is your standard time, correction for meridian, correction for the sun's position, okay. Is that clear? Okay. Let's go further. Okay. If you remember the sign H, we had defined H, okay. The next thing that we need to find out is the computation of solar elevation, okay. So that is, again we have a formula here. Solar elevation depends on sin L, sin D, cos L, cos D and cos T, okay. I'll explain you what are these, okay. Sin L, L is your latitude of the place, okay. Longitude we have already used, so now we are using the latitude. D is solar declination, okay, that we defined earlier with all those pictures you saw, and T is nothing but hour angle. So we'll try to define, this is clear to you, so we have to define D and T, okay. So where does the D and T comes from, okay. Okay, T is the hour angle, okay. Hour angle is between you and the sun, okay, that is on the cycle. So so hour angle depends on to what every hour they change in the 15 degree, okay. So you see here whatever is apparent time which is corrected, see the difference with respect to 12 o'clock, means from the mean C position, if it was right on your head, okay, this 12 will be 0. So how far is in time domain you have gone from 12 o'clock, okay, that will give you the hour angle, okay. So that hour angle, this is your actual time, that may be 11 o'clock or 10 o'clock after having done the corrections. So this way you can get the solar hour angle of the sun, okay. And we also defined the hour angle of the sun earlier, if you recall, okay. So this way you can get the T. Okay, now the declination. We have defined what is the declination, and the method which we use to find out the declination is the following, and declination has to depend on N, okay. Okay, that's the sun's position. So this way you can find out the D, you already know the T, you know the L, so you can find out the sin H. Okay. Can it be negative? T can be negative as well, doesn't matter. But then this one thing I must say, this TA is on 24-hour cycle. Don't write 1 o'clock if you are referring to 1 p.m. but that you will write as 13. That is one thing that you should know. Whatever that comes out to be, so you can find out the T, okay. I worked out one example, so we'll do that example also. Just 5 minutes ago I finished one example, and we'll see that one. So now you are in position to calculate this solar elevation, okay. Clear? So once you calculate the solar elevation, there is a little correction here. Oh no, that's fine. So now we have to ultimately get the R, and that R we need to go back to the table that I had drawn sometimes back and compare this R versus the standard R to say if the solar radiation is high, low, moderate, weak, or things like that. So now you can find out the R, that is 2 by 3 S, which is the solar constant, it means the solar, this is equal to 2 calories per square centimeter per minute. That is the standard thing you are getting. Okay. That needs to be modified depending on where you are and how much is the cloud cover. Because thing which we have not considered so far was the cloud cover. How much is the cloud in the atmosphere? Because that will abstract my incoming solar radiation. Okay. So this is the equation for finding out the solar radiation. 2 by 3 S, which is equal to this 1 minus 0.8 C is a cloud cover. Okay. Cloud cover here, if you recall last time I said cloud cover was 2 by 8 or something, but here remember that 8 is already there. So you have to only see out of 8 how much is the cover. Okay. So suppose you go and outside and say, oh, about if I divide the whole sky in 8 parts, out of 8 parts 2 parts are probably you have the cloud. So this C will be 2. Okay. And this answer what you are getting is in per minute. Okay. Don't forget that, because S is in per minute. Okay. If you go back to your table which you have, where we try to define if the radiation or the insolation is moderate, low, high, that units are Langley per hour. Okay. So to compare this R versus the table that I gave you, you have to multiply this by 60 degrees. Okay. So once you know the R, that depends on many things that we have gone through. Okay. What else the other thing you need? Okay. Whatever thing which you need, let's see, the thing is we started this discussion with the Turner scheme of 1969. Turner says, well, don't worry anything, go to the airport, get some data and you can find out the stability. Whatever we have done, is there any problem getting the data so far? Except cloud cover, that I said to people at the airport, they will collect, because that's very important for them, how much is the cloud cover. So maybe it is little approximation, but I can essentially find out the stability in each hour, and which is very important for me, because all my turbulence depends on the stability. Little complicated in terms of algebra and things like that, but I can do the job. The other thing what you will need is the surface wind. Okay. This R again you compare with the first table which I gave you, the surface wind which was there 2 meters and this and that 6 and things like that. So then I can really find out the stability of the glass. I don't think I should have anything below this, but let's just scan. Okay, see the cloud cover, fine. Okay, this information is enough to calculate the stability class. Okay. So what we'll do is that I have a little example so that you can get better feel of the things. Okay. And so I don't need to have this one, and I can do it on the board, and so let's put this one off. Well, I'll take a little help because I have the real numbers that I went through this morning very quickly just before coming to the class. Okay, fine. I took typical example of Kanpur, for example. Okay, and I said today is what? Today is 28th. Well, I did for 27th. That was a little mistake. So I want to find out the stability at 11 o'clock today, or let's say yesterday. Okay, that is what is the thing. Okay, so what I'll do is that go through this example quickly so that you can understand the thing. So now the objective what we have is find stability. When I say stability, means atmospheric stability at Kanpur at 11 a.m. Okay, all right, on (27,306). That's what is my objective. I found out the longitude and latitude, and then what the other thing you have is the surface wind to 2 meters per second. Okay. Latitude is 26 degrees, okay, and the longitude is 80 degrees. What do you say? 80 degrees east? What do I write? East. And here? Okay. Okay, so the first thing what I did was find out the apparent time. Okay, that is TA. TA is the, well, I don't have the formula, but T, whatever the T standard at the time, plus corrections local minus M standard by 15, okay, plus equation of time, okay, but if you recall, the equation of time was in minutes, so divide by 60. Okay. So what I'll do is quickly I write here 11 plus 80 minus 82 by 15 plus I calculate the equation of time. I'll write it here because to make the things clear. Equation of time was minus 7.7, okay, sine 360. Number of days in the year 2006 will be 365, right? Okay, 365, okay, times, you see it was small n minus 3. So can you tell small n that what that small n will be? Because I am doing finding out 27 March. 86, okay, so we'll write here 86 minus 3, okay, plus 9.5 sine 2 times 360 divided by 365, okay, times 86 minus 80, and that came out to be a very small number. That came out to be and the way the equations are written, all angles you can take them in degrees, okay, okay, so you can specify in degrees. But always remember, when you have a trigonometric function, then all angles are taken in radians. Okay, but this is the way it is simplified and written. You can take them, all of them, in degrees. Okay, if that is the case, I can write this as minus and that came out to be 10.74. Okay, so your time is really not 11 o'clock, but little less than 11 o'clock. Okay, I am carrying in decimal. I am not writing in hours and minutes. Okay, clear? So I got my TA. Then I calculated the solar hour angle. Okay, that was T. I am very close to 12 o'clock. What do you expect the value of T can be? Okay, that was something 15 minus 10.74, or in fact 12 minus TA is 10.74, and that came out to be 18.87 degrees. Okay. Okay. Then I can find the declination. Okay. The declination was, if you recall, this was 23.45 sine 360 by 365, okay, multiplied by 86 plus 284, and that came out to be a small number, approximately 2.0. That was sun's declination. Okay. Okay. Now I want to find what is the next that I find out. What was that? 86 into 86 into 284. Okay, we can check that. Make it plus, okay, n plus 284. What calculation I have done, with plus or with multiplication? Okay, I have done with the plus. So that number 2 is fine here. There is no problem with this number. Okay, now you remember I have to find out sine h. Okay, and for that again I had the formula. This was solar elevation, and the formula was something like this. Whatever that formula was, I'll put the numbers straight because I have got the, that is sine 26 times sine 2 plus cos 26 times cos 2 times cos t. And that came out to be 5.
These are all in degrees.
They all are in degrees. Okay, that I clarified, and they all are in degrees. Okay. Finally, now I am all set to find out R. 2 by 3 times the solar constant S, that I am writing as 2, 1 minus 0.8. I just taken hypothetical that cloud cover is 2. Do I write here? No. Just you can take any number. Maybe in the morning it was a little cloudy, so I took this as 2. So here 2 by 8, okay, sine h. So that is 865. Okay. So that way you can find out the radiation, or the incoming solar radiation or insolation, same thing. And that number came out to be okay, calories per square centimeter per minute. Okay. Okay, now tell me with your knowledge, what do you expect the radiations to be? Too high, too low, moderate? When do you expect the maximum solar radiation? No, solar radiation is around 12 o'clock is high. You expect moderate, right? Because you are talking 11 o'clock, the sun hasn't come up as yet, and the insolation will still increase. So let's see, or this will be equals to 0.46 into 60. That came out to be how much? 27.68. Langley per hour. Now, what category this is coming in? Moderate. And we expected it to be moderate, isn't it? Okay, that is coming out to be moderate. And now go back to the first table where we had the relationship between the surface wind and the insolation. And please tell me the stability. I don't know what that stability is. I expect this to be B or C. Surface wind is 2. Okay, go back to the tables which we gave you about the surface wind and B, and you expect it to be B. Okay, so the stability after going back to the original tables, this stability was for given R and what else? Given R and the wind speed, surface wind. It came out to be B. Okay. Can you suppose you have all the formulas? Now you can find out the stability from anywhere in the world. Okay. For any time of the year, or any time or any hour of the day. Okay. And in fact, this is very extensively used because you can't really find the temperature gradient so easily, because then you have to measure at different heights and do lots of things, which measurement is a routine thing you can't do, and routine thing you can't do at many places. But this method almost you can find out all over the world. You can find out the airport within about 200 kilometers or so. So you can find out the stability. So this is what was the Turner scheme. Very good approach, very good thought that you can very easily find out the stability without measuring any devices and putting the instrumentation and things like that. Maybe slightly inaccurate or estimated rather than the actual number, but you can find out in this way. Okay. What is that we want to do next? Okay. We go back to our basic conceptual model. Okay. We have learned about the sources, okay, type of sources and many other things. Okay. We knew about the receptors. Okay. Now you also know about meteorology. This also is done. Okay. Now objective is to make the connectivity between these three exclusively looking things. Okay. We studied this thing independent. Okay. You agree with me? Without really saying what is the impact on this receptor. Okay. The source, what is the impact on the receptor? We didn't really see that one. We also looked independently, okay, what pollution level a person can suffer, how the vegetation could be affected, how a building could be affected. Okay. And this also we studied independently, okay, what is the meteorology, what is the movement of the air, what is the turbulence and things like that. Although we studied in a very limited sense. Okay. We could have more details of this one. But the objective, if you recall, is to see impact of air emissions from source on receptor by considering the transport mechanism okay, or we can put a word here, assess impact of air emission from source on receptor by considering the transport mechanism, which is your atmosphere. Okay. Now, this is what we want to do, and finally give a solution. If I'll write in little crude language, but that helps in understanding. If receptor is in danger, decide to control or prevent, if you like, prevent S or source emission. Okay. That is what we want to do. But to do this, we need linkages between source and transport, that is atmosphere to receptor. Okay, that we need to develop. And these linkages, the way you develop, and the mathematics of these linkages. Okay, again I'll use some crude English. Mathematics of these linkages we refer to as air quality modeling. Okay, that's what ultimately you want to answer this thing. Okay, so we want to do the modeling part. So we'll use the modeling and apply a little mathematics fundamentals, because physics fundamentals we understand. Okay, we also understand the chemistry fundamentals. Okay, now we apply the mathematics to get the linkages between source and receptor. Okay, so now onwards we will be focusing on to the modeling. And we'll do a very simple model. So if you agree with me, let's call this as air quality modeling. And the first model that we'll develop is called box model. Okay. Something, a box model. Okay. In the box, let's say the wind is blowing. Okay. The speed of the wind is, let's say, u. Okay. And the concentration of the air which is outside the box, let's call that as the concentration of any pollutant which you are considering. Okay. And you are saying the pollutants in the box can disperse only up to a certain height. Okay. What is that height? Mixing height. Okay, very good. So let me call this as Z or mixing height. You can also have some sources which are causing the pollution in the box. So suppose you have a factory, you have the cars, you have the houses, and all cause some kind of pollution. Okay. And then this air will flush out this place and that will go out. Okay. So I am interested in finding out the concentration inside the box. Okay. We apply the simple concept of mass balance. Okay. You apply the simple concept of the mass balance and see the change in concentration. So accumulation inside the box, or accumulation rate if you like, is mass in minus mass out. Mass in will have the two components, outside the box plus inside the box. So let's write this one. So accumulation will be change in concentration, okay, but unit should be mass per unit time. Okay. So on this units I have whatever microgram per meter cube. So suppose if I say this length, okay, is unity. Okay. I can have the many box because the thing will be, I can have n number of boxes, things will be very similar. Okay. So if this box, okay, is this one, then what I can say is the I can take the volume of the box, and suppose this I am calling this as the length of the box, I am calling this is delta x. Okay, this I am taking as 1, okay, unit in the y direction, because it will be the same no matter how many number of boxes are there, depending if the source is the same. So what do I do? U times Z, okay, and 1. Agreed? Okay. 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 Let's check the another thing, if we want to take the reaction or we don't want to take the reaction, because we can even complicate it if you like with the reaction. I think you got it wrong here. We are inside the box, so let's take the box. Okay. Input outside the box. So how much is that coming? C naught times U, okay, times do you agree with that? Concentration, okay, meters per second, okay. So let's check. So this you have micrograms per meter cube, for example. This is meters per second. This is meter square. So what is that you are coming? Coming mass per time, correct? Okay. See, we should write them clearly. I mean, even if you are very good, but go through this thing. Acha, okay. From the box, suppose this emission rate, which is there, okay, I am calling this as QA, okay, that is mass per meter square, okay, mass rate per meter square. So QA, which I am saying as mass per area, per unit area, per second, or time if you like. What is that I multiply this with? Delta X or do we multiply by Z? No, we don't multiply by Z, okay, because mass per unit area is there, okay, the delta X into 1, okay, and you can check that, okay, area cancels, mass per unit, alright, mass per unit time, clear? Okay, plus or minus, how much is it going out is, let's say, is a concentration which is completely mixed reactor, okay. So we are saying the C is a concentration in the box, so that will be, because wind speed is the same, okay, okay, and C is what we are doing mass balance, considering box as completely mixed reactor. Okay, why don't you quickly check if everything is all right? That is fine. This is also fine. Okay. And now you can say the concentration is steady state concentration, okay, that we normally do. So I can put del C by del T equals to 0. Find concentration in the box. Can you quickly do that? Okay, let's do that. You can say C naught minus C times U times Z, okay, plus Q times X equals to 0. So now you have, okay, C0 minus C uz equals to Q delta X, okay. So C0 minus C is nothing but Q sigma X times uz. So C will be equal to, what's that? C naught plus? C naught plus? Is it plus? What are you calling C naught plus C minus C naught? Okay. Okay. So I can say this is C minus C naught. So you should get something like this. Plus C. So that is how you can find out the concentration. Okay. This is correct. Okay. And if you put C naught equals to 0, that you say the prior to pollution coming to the box, the initial concentration was 0. So you can put C naught equals to 0 if you see that one. Okay, I think we'll stop there and slightly talk more about this thing and talk some other standard models which you are aware of. Okay.